Hello and welcome. In this video, we're going to look at how to use Ohm's law in an RL series circuit. Remember that Ohm's law is our Ohm's law triangle. You can draw that out and get your voltage, current, and resistance. Right? And this gives us each form of Ohm's law. For instance, current is equal to voltage over resistance. But now that we have inductors, we don't necessarily just have a resistor with resistance, right? Because that's a linear resistance. We have nonlinear components now, like inductors and capacitors later, that will replace this R here with an XL or an XC, and sometimes even a Z value when we have all of them in one circuit together. And so we want to remember that each one of these resistances can be placed into Ohm's law. That means that we can actually calculate using Ohm's law if we have the resistance that is represented by this impedance here. And so that's really important. If you're using Ohm's law, you make sure that you put in a resistance into your Ohm's law equation. Okay, so to do this, we are going to start off by measuring a couple of our voltages. We're going to go after the voltage drop across the first resistor here, the 6 kilo ohms. Then we'll go after the voltage drop across the inductor, VL, that's the inductor on this side. We're going to use the voltage drop across the resistor and the resistor itself to determine the total current in the circuit. And since this is a series circuit, we're able to use that total current to evaluate the inductor as well. And so we'll use that. We'll use our voltage drop that we get across the inductor, along with the current through that inductor that we found using the resistor, and we'll plug that in to determine the resistance of this inductor over here, XL. It's very hard to measure XL when it's in the circuit unless we go after the actual flow and the voltage through it. So after that, we'll use our other equation to evaluate the calculated XL reactance here. And we'll start there. So the first thing we have to change is this voltage source. This voltage source is actually a square wave, so we can right-click on this and replace this component. And from here, we want to get some kind of power source so that we can use our multimeters. Our multimeters measure in VRMS. And so I'm going to go to power sources and I'm going to get a VRMS power, which is going to be this AC power at the top here. And I'm going to OK that out. And that immediately replaces it in the circuit for me. I want to adjust this down so that it's a little bit smaller than 120 volts. So I'll double click and go to 5 volts here. Our frequency range can go back up. We'll give it like 300 here. We'll OK that out. So now we have a VRMS voltage value that's going to match the voltages that we get from our multimeters. Our multimeters can be found on the top right at the top of our list there. You can click on that, or you can go to your Simulate tab, Instruments, and the first one is Multimeter. So we're going to need two of these, one across the voltage and one across the inductance, or one across the resistance, one across the inductance. And we'll connect the R1 positive probe in front of the resistor and one in the other side of that resistor. And we'll do the same thing for the inductor. We'll put one on one side of the inductor and the negative side on the bottom. If we flip these over, we'll get a negative voltage, right? If we put the negative side to the top of the inductor and the positive side to the bottom, it'll read a negative voltage. So make sure you put them in the right orientation. Okay, so that gives us our voltage. We need to double click on both of these. These are automatically set to read DC volts, and now we have a frequency, right? We have an AC waveform. So we need to make sure that we set both of our meters to AC to be able to correctly measure these two here. And now we can hit play on the circuit and get these two values. So now we know that the resistor has almost all the voltage here. So that's 4.994 volts, and the inductor down there has 251, we'll round that up to a 252 millivolts. Right, that's really small. That's because of this frequency. The inductors like that lower frequency, so they're going to be a smaller resistance when that lower frequency is present. And so we're going to evaluate that as we move forward as well, because these calculations here will allow us to do that in Excel. Now that we have the voltage drop across that resistor, we can use that in our Ohm's law equation. We'll pull that back out, voltage, current, and resistance. It says we want to find total current. So total current would equal our voltage over our resistance, V over R, right? And we know those two because we know the voltage drop across R1 and the value of R1. And so we can plug those two in for that. And we'll say that we actually have 4.994 volts divided by our 6,000, right? 6 kilo ohms, 6,000 ohms. And that's going to equal our total current. So we can do that on our Desmos over here. So that we've got 4.994 divided by 6,000. That gives us a real small current. That's what we wanted, though. we'll see that we can move that back by 2 because it's at that -4 location, and that's not an engineering notation, so we can move it back from this decimal point here back between the 2 and the 3 right here. So that's going to give us an 823. So let's plug that in. Now we have a total current of 832 micro amps. Okay. So with that, we can use that to determine what our inductive reactance is, because now we know that that's the current through the entire circuit. Right? It's a series circuit. There's only one current flow, and that now is 832 microamps. And so now that we know that this voltage here is 252 millivolts, we can compare that to the current using our Ohm's law equation again. Let's get rid of this previous circling here, and we'll figure out how to get resistance. In this case, it's going to be XL, right? XL out of our Ohm's law, and that's going to be XL equals our voltage divided by our current. We just found our current and we know our voltage. And so we can plug that in. We can get our inductive reactance, XL, out of just those two. So we'll send this out and we'll look at that. We'll say that our voltage for that inductor is 252 millivolts. And so we'll move that over. So it's 0.252. That's in our voltage value now, divided by our microamps that we have there, which we can plug that in full into our notation. We can say 832 times 10 to the -6, right? Micro is -6. And so that gives us a 302. So we expect that inductor reactance to be 300 and, we'll round that up, 303 ohms, right? It's now in ohms because we've converted it from our millihenries. We've converted it using Ohm's law. And so now we're going to verify that because our inductive reactance can also be calculated using our inductive reactance equation. And that's our XL is equal to 2 pi FL. Right? And L is going to be whatever value of L we have, including total L, right? So sometimes we have more than one inductor in there, and we have to accommodate for that. But this time we only have one, and we know our frequency. Our frequency is 300 right here, and so we can plug that in for our frequency of this equation, and we can also plug in our 160 millihenries that we have into this one, and we should be able to get somewhere close to our 303 ohms. So let's do that. Send this out, and we'll say that we have 2 pi times our frequency. We know our frequency was 300 hertz, multiplied by our inductor value, which is 160 millihenries. We can move that decimal point back 3 locations and say that it's 0.16. And that gives us, if we round up, 302. So we can say that our XL, when we calculate it out, is actually equal to 302 ohms. That's pretty close. Right? That's what we expect. We expect our measured values to kind of be trailing behind or a little bit above, but they're going to be really, really close. So that's what we wanted to do for that one. So we can also plot these. If we wanted to continue this and check all the different frequencies, we can range the frequency in this and decide which frequencies will be allowed through the circuit, which frequencies would not be allowed through the circuit. Right? And so that's going to be using an Excel plot. So let's go do that. Let's clear out some of this and we'll jump into Excel real quick and we'll evaluate some of these using Excel equations. And then that's going to allow us to put in each of these voltage drops as we range our frequency here. And then we can plot the response of each one of those. So let's move these out of the way up here. And we'll clear out the rest of this and we'll just replicate these equations in Excel and then we'll be able to scale them as we go. So we don't need these two up here. And when we transfer to Excel, there we go. So the first thing we need to do is identify what our circuit is because we do have a couple of parts that stay the same, like our inductor value, our frequency is going to range, and then our resistor value is going to stay the same. And so we can say that our resistor value was 6,000. Put that in first there, and I'll click on that anytime I want to reference that resistor value. We know that our inductor was that 0.16. That was at 160 millihenries. So we'll leave that without any other notation on it so that Excel doesn't get confused when it tries to calculate some of these values out. We have a frequency right now of 300, so we can put that here, 300, and that's going to be in hertz. We're going to leave the hertz off so we can keep the calculation there. We can also scale this up to, say, 1,000 and 3,000. And we can see what happens as we increase our frequency up. And we can even go up to like 10,000 up here to see what happens at even the higher frequencies. That way we have a larger scale. We already found out what happens at 300. So we can write in our VR and our VL for these two here. And we know that that's these two up here. We know the voltage across the resistor was higher, so it was that 4. So we'll type that in, 4.994. And the voltage across the inductor was the smaller one, so that was that 252 millivolts. We want to put that in volts, just in case we have a notation problem in Excel. So we'll put that at 0.252, and that's going to be in volts. So as we increase these, we should see that the inductor and the voltage across the resistor are going to change a little bit. So now that we have those two in there, we actually have this first calculation available. So we can plug that into this right here and say that this is going to be our IT, right? Total current. We also know that we calculated XL in here and that we evaluated XL a different way also right here. So we'll be able to do both of those two and compare them just like we did here. And then we'll scale them through the rest of this values here to be able to scale up our voltages as our voltage measurements change. So the total current here, we can say that this is actually equal to, we'll put an equal sign first, and we'll click on that 4.994 volts that we just put in over here. That's going to call in that term there. We can divide that by what we know our resistor is, which we plugged in at the very top here. And when we enter that out, it should evaluate that for us, right? And that's what we got right here, this really small micro value. They didn't put it in notation for us. We got to move that decimal point up, 1, 2, 3, 4, 5, 6, and then we get that 832 micro. Right, so now we can erase that one and do the next one here. We know that we had to evaluate our XL using our Ohm's law. And so that was going to be our voltage and our current divided. So we can say that this one is equal to the voltage across the inductor divided by the current that we just found using that resistor. We'll set that out, and that's our 302, and that's not rounded up, but we can leave it like that to evaluate it. And we can get rid of that next one there. And this one. And then the last one, we used our frequency at that term. And so that's going to be this first one. We can even call this up here F. So we can evaluate this last one here as well. That one can be plugged in over here. And we can say that that one is our 2 pi. So 2 star 3.14. And we'll multiply that by our frequency, which we know that. That's the 300 over here. Oh, we got to put our equal sign in front. So we'll set equal there, and then that allows us to continue that. So now when we click, it'll add that in. And then we can multiply that by our inductor, and we know that we placed it up here, so that's going to be our inductor at the top here. So when we hit enter out of there, it'll calculate that out for us. Okay. So now we can evaluate what happens when we adjust the frequency. So let's adjust the frequency to 1000 in our multisim. So we'll go back here, and we'll double click on our circuit here. It's actually still playing, so let's cancel that and we'll stop it. We'll double click and adjust this to 1K or 1000, and we'll hit play on that and we'll see what our voltages are. And when we go back into Excel, we can add those in here. We can say that we have 4.931 volts for our resistor and 0.829 volts for our inductor there. Tab that over. These all are going to be about the same, right? So we can just scroll them down one. And then we have to adjust each one of these. We have to plug this resistor value back in for, so that's an A1. This one is going to be these two together, so that one's fine. And this one here has to just be moved back up to the voltage drop there. So we can change that by putting $signs in front of them to force them to stay there. That way they don't move when we drag them down. The A4 we want to move because that's our frequency, so we'll send that out there. That one we want to move, and this one right here we want to keep in place. So we'll put a $sign in front of both of those to make sure that those two numbers don't change. If we put a $sign only in front of one of them, it might scale one of them. Okay, and this one is a part of our equation. So now that we know that, we're going to keep going. We're going to go for our 3000. So we'll adjust this one. We'll stop the circuit, double click, and make this a 3K. Okay that out and hit play on that. And that's our new value. So we'll adjust our Excel document here. Now we've got 3000. So we'll say that we have 4.464. volts, and then we now have a 2 volt, right? We got 2.251 volts. Interesting. So we can highlight all of these, grab this little square at the bottom and drag it down. And now those all worked perfectly because we made those other ones stay in place. And we could do that for 10,000 as well. So let's get our 10,000 mark in here. We'll stop the circuit, double click, and adjust this to 10K. Okay that out and hit play on that. And now we can adjust in, and now we see that's an opposite. We've got 2.556 volts for our resistor, and we've got 4.297 for our inductor. So the inductor now has more voltage. It's acting larger now. We can grab all of these and push this down here. Okay, so this makes it really nice to chart these. We can select this row here and this other row over here by holding Control down and clicking on down, dragging across both of those. After that, you can click into your Insert tab. So from the Home tab, go to your Insert tab, and there's a chart section there that you can click on. There's a drop down even that allows you to place in a line chart. And so we're going to click on that and place that. So this one's a little bit skewed because we don't have very many samples, right? We only had 4 different frequencies. But if you filled all those frequencies out, you'll see that that's a nice smooth line that scales all the way up to the top until that inductor gets all the voltage from the resistor, right? It starts off with no voltage. This is the voltage drop across that inductor. And it scales all the way up until it has all the voltage across that entire circuit. So that's what that's doing, right? It's hogging the voltage when it's at higher frequencies, or lower frequencies gets allowed through. Okay, let us know if you have any questions.